Parametric integration is a section that was missed out of the original edition of the textbook. So unless you happen to have a really new version, you will probably find that these pages don't exist in your book. You can download them from the Edexcel website, or they'll also be on LearnZone in the integration section. There are just two sides, and it includes an example and an exercise along with some answers at the back. We're going to work through a few of them in detail during this presentation so that hopefully you get enough of an insight into what's going on. Because we're working with parametric equations, it will be useful to start by recapping what we know about parametrics from differentiation. So a parametric curve is essentially a set of equations where an additional parameter is included, as well as the x and y that we would traditionally think of as the input and the output variables. We have an additional parameter, and both x and y are determined by the value of, say, t. So in this case, the x-coordinate is e to the power of 2t, and the y-coordinate will be 1 plus t squared. A good way to imagine this is to think about t as changing at a nice constant rate, like time, and then as it changes, the position of an object moves in relation to the x-coordinate and the y-coordinate that is given here. So it might be that one of them is a trigonometric function and oscillates back and forth. If x equals 5 cos theta, like we'll see in a later example, then it's going to go back and forth between 5 and minus 5 over and over again. And if y is something like 1 plus t squared, then it's never going to go below 1, even if t is allowed to be negative, which it can be potentially in different situations. And it's going to get bigger, faster and faster as t gets larger or further away from 0. The key idea that all of this is pinned on is up here in the top right corner. The gradient dy by dx, the relationship between y and x, the rate at which y changes with respect to x, can be constructed without having to combine the x and y equations and get rid of t. Sometimes you're asked to eliminate t to find the Cartesian form, but even if you manage to do that, it can be a real pain to differentiate. So if we can find a way to use the derivatives in terms of t, we make our life a lot easier. And because we can rewrite these in such a way that we can make the dt's cancel, getting the derivative of y with respect to t and the derivative of x with respect to t will allow us to construct the derivative of y with respect to x. The only trade-off is that we get something that involves t. So we'll be able to get the gradient at any point, the standard dy by dx gradient that we all know and love, but it will be in terms of the additional parameter. And that means we'd need to know the value of t to get a particular value for dy by dx. If you need to, I'd recommend you have a go at these questions, you pause the video when you're ready to go through one or check that you're on the right lines, then play the next bit. Question 1, we differentiate both of those. You will need a little bit of chain rule for e to the 2t. Remember, we multiply by the derivative of the inner function, the function inside. E to the t becomes e to the t. So e to the something else will remain e to the something else, but you multiply by the derivative of the something else. In this case, the derivative of 2t is 2. For the other bit, it's a nice straightforward year 1 version. For part 2, the exact value of dy by dx. Now, there are a couple of different ways you can do this, but both of them will require the use of this rule in the top right corner. And the only choice you have to make is whether you're going to substitute t equals 3 into dx by dt and dy by dt originally, or if you're going to do it after you combine them. In this case, substituting t equals 3 in probably makes life a little bit simpler if we do it straight away, but I'm going to show you what happens if we don't do it straight away. Start by writing this out and double check. It's very common to make mistakes with this. Double check that you've got it right so that the dt's will cancel, and then you can write out your expression for dy by dt and your expression for dx by dt, and then flip that one over and multiply the two together, and you should get an expression for dy by dx in terms of t. So this beastie here is dy by dx, and if you give it a value for t, it will tell you the gradient dy by dx. You could also use this to find stationary points. In this case, for instance, because we've got a fraction, if that fraction is to equal 0 to give us a stationary point, the only way that can happen is when t itself equals 0. The denominator of a fraction can never help the entire fraction be 0. It doesn't matter what you divide a number by, you can't make it 0 by dividing it by something. But in this case, all we need is the gradient when t equals 3. So substitute 3 in, and we get 3 over e to the 6. You could write it 3e to the minus 6 if you prefer. And for part 3, the equation of the tangent, all we're going to need to use is the standard formula for the equation of a straight line. And remember, this is going to be the most efficient way. If you're using y equals mx plus c, you have a couple of stages, you have plenty of opportunity to make little mistakes, and you have to work out multiple different things, sub them back in. If you use this formula, all you need is an x coordinate, a y coordinate, and a gradient, and you just put them in the formula. And as soon as you've done that, you're done. You've got the equation of the line. So for this, we're going to need x and y, the coordinates of a particular point. And that's not as tricky as it might seem, because we already have t equals 3. So by substituting t equals 3 into dy by dx, we found the gradient at that point. We can also substitute it into y and into x, and that will give me the x and y coordinates at that point. So that's what we've done here. We found the x value, e to the 6. We found the y value, 1 plus 3 squared, which is 10. And we already have the gradient, 3 over e to the 6. The last line is just rewriting the formula y minus y1 equals m, x minus x1. If you really like, you can go the extra step and expand things out, move things around, but it's not necessary. If they've asked you for the equation of the tangent and they've not specified a particular form that it should be in, then this is a perfectly sensible result to leave it in. The only thing you can do by going further is potentially make a mistake with your rearranging, and then you end up potentially losing marks. If you want to rearrange, it looks something like this. Or this is one of the possible forms you might get to if you rearrange. Now, what does it mean to find the area under a parametric curve? All we've done so far is recap differentiation with parametrics, but now we need to look at how integration would work. In this case, we're working with some slightly more straightforward functions. We don't want to get too hung up on the tricky integration, although that will come in the later examples. We've got a nice quadratic here, and we've got something linear here. It would be possible to find a Cartesian equation for x and y, eliminating t, but as I'll show you in a second, the result of that will be a fairly awkward integration to work with. Not impossible, but a bit messy. So if we can avoid it, it will be helpful for us. The key idea here is built on a very similar concept to what we had in parametric differentiation. Dx is equivalent to dx by dt multiplied by dt. And that's really important because whenever you integrate, you're essentially doing an infinite continuous sum. That's what this integral sign is. That's an S for a continuous sum between limits of x values, and you're adding all of the infinitely tiny rectangles that have an area of height times width. The width is infinitely thin, the height is equal to the y coordinate. Now usually you don't see an integral written in exactly this form because y has already been replaced. If you have the integral of x squared dx, what you're really doing is finding the integral of y dx when y equals x squared. If the function is y equals x squared, then the integral is the integral of y dx, which is the integral of x squared dx. But what's useful about writing like this is that we can recognize even if that function y is written in terms of t, it doesn't necessarily have to be a problem. It would be over here on the left, because if y is written in terms of t, you'll have a function of t, and then you're trying to integrate with respect to x. You've got that dx term in there that complicates things. Since we know we can repurpose things here, we can change the dx into something involving dt, and that is going to end up being really useful because this piece can now be thought of completely separately. We can take that piece apart and say dx by dt is the derivative of x with respect to t. Well, we've got x in terms of t, therefore we can find dx by dt really easily. Dx by dt will be in terms of t, y we already have in terms of t, that's 3 plus 2t, and therefore we'll have an integral that involves just functions of t, and crucially is integrated with respect to t. The only other thing I want to point out here, which is pretty important, is the limits of the integral. We've gone from x equals something to t equals something. And if you forget that, then you're getting a bit of a muddle, because you need to make sure the integral you have perfectly corresponds to the variable that you're working with, the parameter that you're integrating with respect to. everything needs to match, basically. It's a lot like when you do integration by substitution. When you substitute, you need to make sure every trace of the x, any function of x, gets removed, replaced, the dx gets replaced, and the limits, if there are any limits, need to change from limits in terms of x to limits in terms of your new parameter. So let's work through this one. The area enclosed by the curve, the x-axis, and the lines x equals 1 and x equals 13. So those are our limits, 1 and 13. And the function is y, so we're integrating y with respect to x. But because we have y in terms of t, we know we're going to need the parametric version. So all this means is you divide dx by dt and you simultaneously multiply by dt. And that effectively converts your integral into one that's now in terms of t. You'll notice I've managed to magically construct some t values. Those come from the x values and also from the original equation linking x and t at the top. X equals 1 plus 3t squared. So if x is 1, then 1 plus 3t squared is 1, and that means t has to be 0. For the other one, there's a slight subtlety involved in that one. If x is 13, then 1 plus 3t squared is 13, which makes 3t squared equal to 12, t squared equal to 4, and so t is equal to 2 or negative 2. There are two possibilities there, and that's something to be aware of and be careful of depending on the situation. In this case, the detail that we probably ignored initially comes in really useful. T is greater than or equal to 0. So although if t were allowed to be negative, there will be two different moments when the curve reaches a particular point. In this case, there is only one. T won't be negative 2 because t is greater than or equal to 0. Therefore, t must be 2. Now we substitute in the expressions for y and dx by dt. Y as is, so 3 plus 2t, and then dx by dt, that I've just calculated on the fly here, but that comes directly from x equals 1 plus 3t squared, therefore dx by dt must be 6t. If it's more complicated, by all means spend an extra line writing down dx by dt and calculating that precisely. Take care you don't try to squeeze too much into one particular step because you're likely to make more mistakes. Now, all we need to do next is expand the brackets so we've got something we can easily integrate. You don't want to be dealing with a product inside an integral. You could, in theory, deal with this one using integration by parts, but it's going to be a real pain, and it's almost always better, if it's at all possible, to get rid of any products. Leave ourselves with something nice like this simple quadratic, and then integrate directly. We get 18t squared over 2 and 12t cubed over 3. Then you substitute your limits in. And you'll notice the limits are the limits for t. We don't ever have to convert back into x's or anything like that. We can keep everything in terms of t, and we generate our result, 68. One quick note, if we had converted this into Cartesian form, this is what it would look like. You'd end up having to get y in terms of x, which is even messier than just finding some general Cartesian form. And because of all those awkward squares and square roots going on, it would make this integral a little bit messy. Not impossible, I mean, you've got standard results for it, so it would be perfectly doable, and I'd recommend if you want to give it a go, try it, see if you can come out with the same answer of 68. But I think you'll agree afterwards that the parametric version is a bit more efficient, and certainly when you've got more accustomed to the idea, you'll feel more comfortable with it. The next thing to try is some of the questions from the textbook insert. Just have one note to make. There is a slight typo on question 2. The limits have inequality signs written the wrong way around, so watch out for that. You probably wouldn't notice it unless you were being very particular and careful, but since I would like you to be particular and careful, I'm hoping some of you would have had an issue with that unless I pointed it out. Give those a go, and if you get completely stumped, don't worry, because they're the next thing I'm going to talk through. If you need to pause and try some of those questions, do so now, and then come back for the next few. We're going to work through questions 2, 5, and 7 as examples. Question 2. X and y are both given as trig functions, sine t and sine of 2t. T varies between 0 and pi by 2, or 90 degrees. It's worth saying before we dive in, it can be helpful to get a feel for what's happening. Try to imagine tracing out this function so that we can see which x and y values correspond to the t values. It's fairly quick in this case. we can see that when t is 0, x is 0 and y is 0, so we must begin at the origin when t is 0. And then as t increases, x increases because sine of small numbers are small positive numbers, and they're both sine of 2 times t. So we're moving in this direction. We can also see, if you think carefully, x is going to vary between sine of 0 and sine of pi by 2, or sine 90, which is 1. So x goes up from 0 to 1, and that seems to be what's happening with the graph. At the same time, y is going from sine of 0 to sine of 2 lots of pi by 2. And along the way, it's going to go through sine of pi by 2. So it goes from 0 to 1, back to 0 again. And that's why it looks like the maximum point here is going to be a 1. Now, that didn't take a huge amount of time, but it's immediately given me a rough idea of what the area should be. I can see that the width is 1, the height is 1, and it looks like I could reasonably approximate it by imagining a triangle stuck inside. That triangle would have a width of 1 and a height of 1, which gives it an area of a half, and my curve is obviously a bit bigger than that. So a half is my lower bound, but I wouldn't expect the area to be much bigger than 0.6 or 0.7 because it's pretty similar to that triangle that I'm imagining. So I've immediately got a rough idea of what I expect the area to be. And then we can dive in and start working out the integral. The other thing that's happened that's useful here is I already have an idea of what the intercept is with the x-axis. So that's the first job. You identify the limits for your integral, and sometimes those limits are more obviously recognized in terms of t or theta, but sometimes it's easier to see it in terms of x first. So we can identify more rigorously, if you like, where the curve cuts the x-axis. That happens when y equals 0. So solve sine 2t equals 0 within the range, and we find there are two values. Because we're solving sine of 2t, I consider the modified range from 0 to pi for 2t. I find solutions for 2t within the range, then I divide by 2 to get solutions for t. Each of those corresponds to its own value for x. If I put t equals 0 into x equals sine t, I get 0, and if I put pi by 2 in, I get 1. So I can see that 0 and 1 are the values either side of the range that I care about. Then we set up the integral, and then we rewrite it into parametric form. Between 0 and 1, we have y dx, but then in order to write parametrically, we divide by dt, and we multiply by dt. At the same time, I've converted my limits to limits for t. We've already got these. If you think about it, we found them up here. The 0 and the pi by 2, they correspond to the beginning when we're at the origin and the end when we're at the point 1, 0. So we can use those directly from the previous part that we worked out. And then we substitute the expressions in for y. Y is sine 2t, and for dx by dt, which comes from sine t. So if x is sine t, then dx by dt will be cos t. And the next bit is the integral. Now, the original example I went through had a nice straightforward integration, so you'd done the bulk of the work by the time you got to this point. But often, they will, in exams, they'll try to test you on a range of different things from integration, and a lot of the things that you'll be using parametrics for, if you go on to use them in physics or astronomy or engineering, places like that, the integral here may be quite a messy thing to work with. It might be the sort of thing where once you've managed to construct it, you need to find some clever tricks, or you need to potentially resort to numerical integration methods to get an approximate value. But the parametric situation is most commonly found when you're dealing with real life situations, when x and y are literally determined by the time that goes by. And it's easier to think in terms of parametric than it is to think in terms of Cartesian directly. Now in this case, I'm going to do something clever at the beginning. It looks like I've just shifted a 2 around, but if you think carefully what's happened, sine 2t is a double angle, and I would like to find a nice way of dealing with the entire integral. This may not be the only way to do it, but it seemed like the most obvious to me. Sine 2t can be turned into 2 lots of sine t cos t, and that's what I've done here. The only difference is I've also multiplied by the other cos t that was kicking around. That gives me an integral which looks like the kind of form I can deal with. Now, the more practice you get with this, the more confident you'll be noticing this for yourselves. But the fact that I've got cos squared t and it's multiplied by sine t means that my immediate thought is that I can use a substitution. Some people will do this by inspection as well. It's one that you could argue is one of the inspection results in the book, but I find they can be a bit hard to get a handle on and complete while feeling confident exactly what my answers are. So I usually do a formal substitution. How do I know that that's a good idea? Well, I've got cos t that's been squared, and whether it had been squared or cubed or any other power, I could still use this idea. The fact is the derivative of cos appears in some form as a factor in the integral. Cos differentiates to minus sine, and we've got a sine t right there as a factor, which means it will cancel nicely. We'll get du by dt equals minus sine t, so we'll end up with du over sine t equals dt, or minus dt. And we can replace dt and we can cancel out the sine t. I've left that for you to work through for yourselves a little bit, but this is where we should end up. And there's one other thing that's really, really important here. When I originally had the limits as x equals 0 and x equals 1, they first got converted to t equals 0 and t equals pi by 2. And I've explicitly written them out with t's because by the time I get to here, using a substitution, we have a whole other variable involved all over again. And in order to identify this clearly, I need to make sure I convert the limits again. I need everything in this integral to involve u, not t. So we'll get cos of pi by 2, the previous limit. And that happens to be 0. So it might look a little weird that you've got an integral from 1 to 0 instead of 0 to 1, but it's all taken into account by the variations and the adaptations that that substitution does to the integral. Think of it as distorting a graph. If you stretch it or squash it, then the upper limits and lower limits will probably preserve their relative ordering. But if you reflect it in some way, it might be that the upper limit becomes the lower limit and vice versa. All that's sorted out for you. You don't need to think about it. It just happens, provided you stick with the order in which the limits came. So if the upper limit was t equals pi by 2, then we'll have an upper limit of u equals cos of pi by 2. Now, like I said, this sorts itself out quite nicely. Cos squared t will be u squared. The 2 is there. The negative appears because the derivative of cos is minus sine, but it all finishes off quite well. You substitute in the 0 and the 1, you get them the right way around, and as you can see, the negatives cancel out, and we get an answer which was pretty much what we were expecting. We said 0.6 or 0.7, well this one's 0.67, so pretty happy with that. Question 5. This one involves trig again. This has a cos and a sine, and we can briefly get a sense of what's happening again by considering what 5 cos theta does as theta varies between 0 and 2 pi. Cos theta goes between plus and minus 1, and 5 cos theta therefore will go between plus and minus 5. We can see straight away then that our graph is going to vary between 5 and minus 5 in the x direction, and similarly in the y direction we'll have a 4 and a minus 4, because sine theta goes between 1 and minus 1 as well. When that happens, that's a little more subtle. We need to think about what cos theta does. Cos starts at 1, which means that x starts at 5, and as it goes along, it goes down to 0, which maybe is going up and maybe is going down, that's not clear yet, and then it goes to minus 1, which is there. So all we're looking at right now is the x direction. Starts at 5, goes to minus 5 and back to 5 again. While that's going on, in the y direction, we have starts at 0, and then goes up to positive 4, and then down to negative 4 and back to 0. So up to 4, down to negative 4, and then back to 0. That means that as t changes from 0, we're starting from the point 5, 0, and we're moving anti-clockwise around this ellipse. That'll give us some sense of what's happening as we go, and it'll also help us to see why the t values we get seem to be in a funny order. The far right x coordinate corresponds to an earlier t value than the t value we'll get at p. Okay, but this question comes in a few different parts, so it's going to take us a little while. We're going to break it apart into a couple of slides. Part A says find the gradient at the point P where theta equals pi by 4. Well, If we want the gradient, that means dy by dx. So we need to find dx by d theta and dy by d theta. When we've got those, we combine them using that what's sometimes called the chain rule, where you multiply the derivative with respect to one thing by the derivative with respect to something else. And this is what we get. We've got those two separate derivatives, minus 5 sine theta and positive 4 cos theta. We need to multiply by d theta by dx, which means we're flipping the minus 5 sine theta over. And although you could call this minus 4/5 cot theta, and some of you might have done, because we're going to be subbing a number, and I've left it in terms of a reciprocal of tan theta, because I'll find that easier to visualize in my head. We're putting in theta equals pi by 4, and tan of pi by 4, that's 45 degrees. Tan of 45 is 1, so we should get minus 4/5. We can verify that by looking at the graph. It looks like it's a negative gradient, so that seems plausible at least. We don't have enough information perhaps to say exactly what it should be, but it certainly looks from the picture like it should be a negative gradient line. For the equation of the tangent, we're going to need the x and y coordinates, but we've already got the gradient at that point. So we just need the x and y coordinates at the point P. And what we know about the point P is that at the point P, theta is pi by 4. So we just sub that into x and y. 5 lots of cos pi by 4 and 4 lots of sine pi by 4. They give us the x and y coordinates, and we need to keep them in exact form because we're looking for exact answers. We can see that because in part C it asks for the exact area of the shaded region. We're going to need something precise. An equation of the tangent is not going to be an equation of the tangent if instead of writing 2√2 you've written 2.8. In fact, no matter how many decimal places you use, that number is not the same as 2√2, so technically, and it may seem picky, but it matters if we're looking for exact values, we need to use only a value which corresponds exactly to the value we want. The last step is just substituting into this formula. There's nothing different happened apart from my value for y has been put in as y1, my value for x as x1, and my value for m as m. And like we said before, there's no need to use any other formula for straight line equations. Once you've got a point and a gradient, this is the formula you should use. There's no further working needed. I'm not going to do anything further with it. I'm going to leave it in that form. For part C, we need to think carefully about how we're going to find this area. And by looking closely at the diagram, hopefully we can see, if we consider this as being a triangle with a little piece of curve cut out from it, we might be able to recognize how we're going to do this. If we get the total area of the triangle, we can subtract from it the area of the curve, and then we should be sorted. It's important to have a bit of a game plan here, because once you get bogged down in some integration or messing around with algebra, it's easy to forget exactly what you're aiming for and perhaps stop too soon or not recognize when an answer doesn't make sense because you haven't got the big picture clear in your head. So make sure you know what you're going to do and maybe write it down explicitly at the beginning, like I've done. To find the shaded region, we need the area under the triangle minus the area under the curve. Now I'll break it apart. We'll do the triangle first. In order to get the area of the triangle, we're going to need to use half base times height. That would be the easiest way. We can see it as a right-angled triangle. My diagram's not very clear, but I've dropped a perpendicular down to the x-axis from P. So we have a right-angled triangle that we're looking at. And if I have the base and the height, I can multiply the two, divide by 2, and I'm done. I've already got the height. That's the y-coordinate of the point P. I worked that out previously when I was trying to get the equation of the tangent. So you can just read that off from your working for part B. And as long as you've made that clear and you've labeled things, that saves you a lot of time. To find the base width, that's going to be a combination of the x-coordinate at R and the x-coordinate at P. We'll need to subtract one from the other because we're just looking for that distance from P to R horizontally. We've already got the x-coordinate of P. Again, that was from part B. For the x-coordinate of R, we need to think, what do we know about R? R is the point where the tangent touches the x-axis. And the x-axis is the line y equals 0. So we're going to set y equal to 0 in the tangent equation that we've already got. If in doubt, or if you get stuck in complicated part C, always look back at parts B and A and ask yourself, are there any clues? They've asked me these questions for a reason. Chances are there's going to be something useful about them, at least one of them, that I can take advantage of to help me with the question I'm on. When we make y equal to 0, Remember, my equation wasn't in a particularly pleasant form, but setting y equal to 0 just means that y disappears from the front of this equation, and I've got something I can now rearrange and solve. Once you've rearranged it and solved it, it's worth double checking. Go back, check it in the calculator, see if subtracting 5 root 2 over 2 from this number and multiplying by minus 4/5 really does give you minus 2 root 2. Your calculator should be able to verify that for you. The other thing you can do is check that it's sensible. If we look at the diagram, if you recall, we said it goes from 5 to minus 5 in the x direction. Well, having an r value at 5 root 2, which is getting on for 7 and a bit, that seems like a perfectly plausible place to be. I think we're at 7.1 or something. That looks reasonable as far as this diagram is concerned. The diagram won't be perfect, it won't be exactly to scale by any means, but that gives us a good idea. It's bigger than 5, so ballpark, we're on the right lines. Next, we can use that to get the base of the triangle. Don't stop at 5 root 2 because you will not be correct. In fact, if you put all this information on the diagram, it's much easier to see if you made some silly, easily avoidable mistake. We need to look at the x-coordinate at r, which is 5 root 2, and the x-coordinate at p, which is a half of 5 root 2, and subtract one from the other. So we end up with half of 5 root 2 for the overall triangle base. Now we've got the triangle base and we've got the triangle height already. We're going to combine those two things, and that should give me the area of the triangle. Half base times height, all the awkward surds cancel out as it happens, and we get an area of 5. And again, you can check that this is reasonable. It looks like it's a fairly sensible area to have, just rough. Now we've found the area of the triangle, we need to look at the area under the curve. Then we're going to subtract it from the area of the triangle. This is the bit that needs parametric integration, and we need to first identify the limits. Fortunately, we've already looked closely at what's happening with x equals 5 cos theta, so we should be able to recognize that the value where the ellipse crosses the x-axis here is going to be a 5. We've already got the x-coordinate at p. We calculated that in one of the early parts, in part B. I think it came out as 2 root 2 or something like that. But we can do this more formally as well. The curve cuts the x-axis when y equals 0, and that gives us theta equals 0 or theta equals pi. Now, we could take the 5 that we got for the x-coordinate and put it into x equals 5 cos theta, and that would allow me to rearrange. We get cos theta equals 1, therefore theta equals 0 or 2 pi, for instance. Now, I've done it a bit backwards here. I'm saying if the curve cuts the x-axis, what theta values does that occur for? There are two different values where that happens within our range, and if I try both of them, when theta is 0, I get 5, which is what I'm expecting. But if we try theta equals pi, we get another sensible looking answer, minus 5. That's what we would expect to get if you think about it. All we've asked is when does the curve cut the x-axis? There are two valid answers, and this has given us both of them. But we can see which one we care about. We need the one where theta equals 0. That allows me to jump straight to putting the limits in terms of theta instead of in terms of x. I've got theta equals pi by 4 because although I have an x-coordinate for p, I don't need to use that x-coordinate. I just end up going back to pi by 4, even if I make no mistakes. I just get back to what I had before. We already know that at p, theta is pi by 4. And we know that at the point where the ellipse crosses the x-axis, theta has to be 0. And remember, we said that this might be a little bit strange and backwards. If we start from 5 and we're working anti-clockwise around this ellipse, which is what happens if x is 5 cos theta, we're varying from 5 to 0 to minus 5 to 0 to 5. And at the same time, y is going from 0 to 4 to 0 to minus 4 to 0. So we're going anti-clockwise around the ellipse. And that means that we start at x equals 5 and we finish at p. And that's why these limits may look like they're a little bit backwards. We just need to make sure we preserve the order of whatever the x value limits were. If we do that, everything will be fine. So don't panic if you end up with an integral where your limits look like they're backwards. Don't change them just because they look like they're backwards. Sometimes they need to be. Now we have the integral of y dx, but we've already divided by d theta and multiplied by d theta. That allows me to write this all in terms of the new parameter theta. And if we put the expression for y in, 4 sine theta, and then we differentiate x to get dx by d theta, we have minus 5 sine theta. And if we combine those and simplify a little bit, we've got minus 20 times the integral of sine squared theta d theta. I've pulled out the minus 20 to make it look a little simpler. It doesn't really matter if you do that or not, or if you pull out just a bit of it, as long as you don't forget that you've got a negative 20 involved as well. That allows me to look at it a bit more clearly and recognize I'm dealing with the integral of sine squared. And every time you have the integral of sine squared or cos squared, you'll be using the same technique. We look at the cos double angle formula, which can be variously written, and one of the forms it can be written in is this form. It's cos squared minus sine squared, and if you don't immediately remember that or which way round it goes, derive it from the cos a plus b formula in the formula book. But when you've got that, replace either cos squared or sine squared with 1 minus the other one squared, and you can construct either 1 minus 2 sine squared theta or 2 cos squared theta minus 1. With a bit of rearranging, you can replace sine squared theta inside an integral with something involving cos 2 theta. And it may seem like that's equally complicated, but from an integration perspective, integrating something involving a multiple angle like a cos 2 theta is much easier than a squared or a cubed trig function. We can just use the sort of basic chain rule or inspection protocol here. So cos 2 theta will integrate to sine 2 theta over 2. And the 1 integrates to theta. I've got a minus 10 instead of a minus 20. That's because when you rearrange, you get sine squared theta is 1 minus cos 2 theta over 2. So I've pulled out the half as well. At the end, when you put it all back together, we get an answer 5 pi by 2 minus 5. And it's worth checking. Just check for the basics. Have we got a positive value? Because if we haven't, we've made a mistake. And if you get that sort of thing, if you get a negative when you shouldn't, don't just stick a minus in front and hope for the best. Go back and find where the mistake happened, because otherwise all you're doing is making an additional mistake on your final line, which is not going to play very well for exams. The final part that you need to not forget is that we need the shaded region. If you've already written out at the beginning what you're trying to do and you make sure you reread the question at the very end, that will remind you what the big picture is. We've found the area under the curve. We already know the area of the triangle. That was 5. So we subtract 1 from the other and we get this area, which is about 2-ish, which seems reasonable given the size of the graph. Question 7 is also trig. We've got x equals t minus 2 sine t and y equals 1 minus 2 cos t. It's worth thinking a little bit about what this function will do. We can see, for instance, that in the y direction, because cos varies between plus and minus 1, 2 lots of cos will vary between plus and minus 2, negative 2 lots of cos will vary between minus and plus 2, and if you add 1 to that, you get something that goes as low as minus 1 and as high as positive 3. So it looks like we'll get a value of 3 here and a value of minus 1 here. That'll be handy if we're trying to estimate what the areas will be later on. We can also do something similar with the x coordinates, but we start with part A, where they ask us to show where the curve crosses the x-axis. That's exactly what we'd be interested in looking at anyway, especially if we're trying to find the area of the shaded region. So every time you see curve crosses the x-axis, it's the same deal. The x-axis is the line y equals 0, so we replace y with 0, and we see what happens in here when we put y equals 0. We're going to solve within the range 0 to 2 pi, and that should be reasonably quick and simple. We get pi by 3 and 5 pi by 3. What's worth noticing here is what happens to x at those different values. This is a bit more detail than you necessarily need, but given that part B is a show that question, you want to make sure you can justify each step. When t equals pi by 3, x will be pi by 3 minus 2 lots of sine pi by 3, which gives pi by 3 minus root 3. And then if you put in 5 pi by 3, you get 5 pi by 3 plus root 3. This means that we can see the positive x value must correspond to this point on the graph, and the negative x value, pi by 3 is about 1-ish and root 3 is about 1.7-ish, so we can see that's going to be a negative. That corresponds to the negative x coordinate. That is also helpful because it shows us that the relevant t values, they correspond to those same places. So if the leftmost x coordinate is pi by 3 minus root 3, then we need the lower limit to be pi by 3 and the upper limit to be 5 pi by 3. That's how we construct the integral. We put pi by 3 and 5 pi by 3 for the limits, and then I've immediately written here, instead of y dx, we got y dx by dt multiplied by dt. So the dt goes in straight away. You can do it all in the same line. And then we just need to replace the y section by whatever y is, and the dx by dt section by the derivative of x with respect to t. That does simplify. As you can see, those two just happen to come out the same, so we get something squared. And that may make you think, oh, there's a nice integration result I should be aware of that can deal with the square of a bracket involving trig. Well, there may be other ways to deal with this, but I've found the simplest approach that I can use is generally the one that I understand and am most familiar with, because I'll be much quicker with that than trying to mess around trying to find some alternative magic method. If I expand things out, I end up with something where most of it I can deal with straight away. Constant, I'm happy with. Minus 4 cos t, I'm happy with. And 4 cos squared t, I don't have much of an issue with because, as in the previous question, anything with a cos squared or a sine squared can be turned into something involving cos 2 theta. That comes directly from the cos 2 theta formula, which, if you're not familiar with it, you can derive from the cos a plus b formula in the formula book. It gives you cos squared theta minus sine squared theta. But because cos squared plus sine squared equals 1, you can turn it into something that involves only cos squared theta or something that involves only sine squared theta. I've done the only cos squared theta version, and I've rearranged a little bit so that I can directly replace cos squared theta with something involving cos 2 theta. It may not seem simpler, but it's really easy to integrate cos 2t, and it's not easy to integrate cos squared t. So that's what's happened here. The 2 cos 2t plus 2 is what happens when we multiply this expression here by 4 to get the 4 cos squared t. We can put that 2 and that 1 together, of course, but I'm not going to waste a whole line doing that. I'm going to jump to the integration. We end up with 3t minus 4 sine t, and then this bit is 2 lots of sine 2t divided by 2. So the 2 that was there ends up cancelling when we divide by the derivative of 2t. It's a function of a function, which in integration can be tricky, but as long as the interior function is linear, we can just use the simple reverse chain rule. We can divide by the derivative of what's inside. When you substitute your numbers in, we get this, 4 pi plus 3 root 3, which you can check on your calculator is a reasonably large number. 4 pi is about 12, root 3 is about, well, just under 2, so 3 lots of it is going to be a little under 6. We're looking at 17 or 18, something like that for the area. We can check that that area is sensible if we've already got these values that we looked at before for x and for the maximum value for y, which we've already got on here. So if you want to get a rough idea, let's sub those in. If we do 5 pi by 3 plus root 3 and we subtract pi by 3 minus root 3, that will give us a pretty good idea of what the width is. So the distance across from here to here, that comes out as approximately 7 or 8. We'll call it 8, closer to 8. And the height is, of course, 3. So if you want to get an approximate value for this area, we could have done that as soon as we found the x and y coordinates of these relevant places. 8 times 3 gives an approximate area of 18. That's just a rectangle, which looks like it should enclose the entire piece of the curve that I care about. So our area should come out to a slightly smaller number than that. Remember, this is just an approximation, something to give you an idea of whether you're on the right lines. I get 17.7, so apparently it's pretty close, but bear in mind we've done a bit of approximations here. That's a pretty good result. That shows us we're on the right lines. We've got what we were looking for. The last thing I want to point you in the direction of is an exam question on parametric integration. This one does not involve trig. This one involves some logs and a little bit of partial fractions. There is a link in the document. The document itself is in the Year 2 integration section of LearnZone. And the document, when you download it, has got a link in it to solutions, which are on, I think, examsolutions.net, and also a solutions video. So hopefully that'll help you to get to grips with the rest of this topic. Plenty more questions in the exercise in the insert sheet that you can download. And as always, if you have additional questions or you want to discuss with your classmates or your teachers, upload your questions and photos of your solution attempts to the forums, and we'll be able to help you out.